We will go through about project location, climate study, site analysis, design concept, assessment method, and the simulation. We position part of their structure to change their appearance, to create different usable space to respond environmental condition. It's a kinetic side, so it's designed to move with the movement of the wind and to create constantly changing visual effects. Depending on the weather, wind is coming from the now strong or gusty. The wind is so the way it does not by arraying about 130,000 small aluminium panels that pivot into panes and panels move individually. So the overall effect is basically being able to see wind in the same way that you would even moving across to the ocean or large body of water. So the panels are individually assembled in the rails, and those rails from a large kind of structure that were all insulated from inside to the side into a large structure or farmer and nothing to them. The study aims to design a dynamic architectural building that can respond to daily change of the environment factor. It should take in consideration the location of the project, which is Munich in the case of the administrative building. Should be proper control in the sun shading pattern. It should control in the ventilation and to design to achieve the comfortable outdoor environment and to respect the surrounding. So to achieve also the energy efficiency using sustainable materials. Munich, located in southeastern Germany, 500 meters above sea level, Germany is one of the leading countries in the field of energy. We choose Munich because it's one of the cleanest countries and it's considered globally in the field of energy and sustainability. The stage has been set while searching for a good plot in urban center of Munich. It has been remarked that there is no free space in all city. All parcels were occupied either by building or green spaces structure. So our plot was found in semi-urban area located between the historical urban and the rural zone of Bavaria. The diversity of area between residential, commercial, industrial at the same time, and we can see the mix between the rural urban and the urban zone. And the dimension of our site is the length is 210 by 40. Winter and mild, pleasantly warm summer. In summer, comfortable and wet. In winter, it's very cold and partly cloudy year around. The temperature is typically between 25 Fahrenheit to 75. The wind direction is coming from the northwest. The air quality in Munich is considered as good. There is no air pollution depending on the air quality index AQI. Our site considered as a mixed-use site. We have hospitals, sport, business offices, green area, entertainment like restaurant and cafe, educations and shops. Munich could be advantage during summer as doesn't require artificial cooling solution to achieve temperature and comfort. However, the cold weather from 6 months appear in the year, so the design challenges would be to need more energy consumption for heat gain to reach the comfort zone in winter. July is the hottest month in Munich, average temperature 17.5 Celsius, and the coldest is January -1 Celsius. The wettest month is May, average have 40 mm of rain. Munich considered as a windy area. The wind appear like 5 months from November to April. It's have normally breeze velocities more than 6.5 miles each hour. The windy month is January, reach to 7.6 miles each hour, and the climate month is August, have normal speed 5.4 miles each hour. Most part overcast 64% of the time. Winter in Munich is cold. Temperature have near to freezing, and rain and snow are common. In near area, the rainfall is reached to 1000 mm. 13 out of 31 days in Munich are snowy days. The office building was designed based on simple compact cubic volume which tend to be rounded on south side to reflect the sound wave coming from the train station that could cause acoustic discomfort. Of brick building were chosen based on German regulation requirement. Project is a 3-floor building with a capacity of 600 employees. It divided into 24 offices, 2 meeting rooms, 1 cafeteria and stationary space for each level. For the building assessment on IAS, materials were chosen based on European regulation that recommended a minimum U value. The initial simulation in IAS showed that the building has a very bad quality of daylight and ventilation due to the competence. The inner surfaces are dark while the outer space have a glare. An improvement was made in the design by integrating an atrium to increase the daylight factor in the building spaces and to enhance the quality of air inside. Here we started the journey of efficient case, which aimed to achieve indoor comfort of the design. To improve the indoor condition of the design, the Passive House Guide for Building Assessment Regulation was taken as a reference. It is principle based on radiation control glazing, shading and daylight, mechanical ventilation with heat recovery, high performance insulation, thermal bridge elimination, airtight construction. To reach the maximum energy efficiency, we assess different orientation of the building. The Passive House Regulation, the atrium will increase daylight factor inside the building and enhance the quality of air by increasing the movement of the integration for more glazing in the facade will participate in daylight enhancement. However, this will increase the glare issue and solar gain during summer. That's why we have the necessary to use the kinetic shading elements.
Our kinetic facade is a biomimicry design inspired by the butterfly and its wing movements. The mechanical system is composed of 2 wing units, which are rotating around its axis in different angles of opening to ensure certain climatic conditions for the building indoor space. Technically, the kinetic facade system could be applied by using 2 rotor elements, which are the wings and the stator around which the wings will be turning. The wing units are to be manufactured from a lightweight material which blocks solar radiations and allows natural daylight at the same time. However, the stator must be made of solid metal as it is the structural part of the system. To find the most suitable areas for shading elements, IAS software was used to analyze the sun exposure of the building during the whole year. Areas which receive more than 700 kWh per meter square were selected for shading installations. For maximum thermal insulation, the building materials configuration will respect the U value required by the Passive House Regulation. After suncast analysis, 3 scenarios were defined for simulation: winter, spring, and summer scenario. For each scenario, 3 times of the day will be used for simulation. Regarding total system energy, the efficient case could reduce the building system energy with 14,000 MW per hour. The use of kinetic facade decreased the total solar exposure of the southern facade from the range of 800 kWh per meter square to the range of 400 kWh per meter square. Daylight factor was significantly increased in the heart of the building due to the atrium integration. The winter simulation shows that the use of kinetic facade keeps the air temperature of the rooms in low values, which doesn't permit to achieve the indoor thermal comfort. Thus, Keeping the wings of the kinetic shading in 90 degrees will allow a comfortable air temperature in the building spaces. Same remark regarding solar gain simulation results, which favorize the use of shading wings in 90 degrees. Visual comfort was achieved by the elimination of glare through the use of kinetic shading on the southern facade. The indoor space illuminance was decreased by the shading elements use. The psychometric chart of winter simulation shows how could the design improvement participate in achieving indoor space comfort. However, from the results, we conclude that no need for kinetic facade in winter. It was remarked that the kinetic facade enhanced the daylight factor in the southern spaces of the building by decreasing the exceeded light amount penetrating the indoor spaces. In spring, visual comfort was achieved by the elimination of glare using kinetic shading on the southern facade. However, the result shows how is the degree of opening in the kinetic facade important and sensitive for better comfort. The psychometric chart of spring simulation explains also that the shading will decrease indoor building comfort. The summer simulation results show the efficiency of kinetic facade shading in controlling solar radiations penetrating the building indoor spaces. Moreover, the percentage of shading plays a significant role to achieve the visual and thermal comfort. The results show here that increasing the shading percentage helps to achieve indoor comfort by decreasing solar radiations entering the building. The illuminance ratio was decreased significantly in the summer scenario by using kinetic facade shading. Simulation results for wind velocity and pressure show that the site has a good potential of wind energy production, as there is a significant pressure difference in the site and a minimum velocity of wind which is enough for wind energy production during the whole year. Internal wind velocity and temperature were also improved with the integration of atrium and kinetic shading facade. The summer simulation results show the efficiency of kinetic facade shading in controlling solar radiations penetrating the building indoor spaces. Moreover, the percentage of shading plays a significant role to achieve the visual and thermal comfort. Kinetic facade are smart solutions for smart buildings, which will achieve the space, comfort, energy efficiency, and sustainability.